practical purpose of that class. The purpose of that class is to become money. I rated that way. When will I ever use?
I've audited those. I like it.
When will I ever use English way?
The only thing I don't like out of this book is Shakespeare. Shakespeare can go dig some grave with him.
Okay, it's 9:30. Let's start. Thank you for being here. So this week class would be the most difficult part of your syllabus.
Oh, no.
Okay, so I request you to pay attention. And I will try my best to make it as easy as possible. And if you pay attention, I can assure you it would not be difficult. And this is the one part where many students who takes algorithm course, they are familiar with P, NP, this term, but majority do not understand it. What is the difference between each one of them, and or what are the relation in between them? Okay, so please pay attention. So last day we mostly talk about approximation algorithm, right? And so let's briefly talk about what is NP complete problem. We define informally. We still did not define it formally. Yes, thanks. So what is NP complete problem?
Problem that has no time efficient.
Algorithm exists. Time efficient means no polynomial time algorithm exists so far, which will solve every problem, which will give you exact solution for every instance of that problem. But please remember, this is an informal definition, not actual definition. We'll come to that actual definition later. So still it's an informal definition. What is that? There is no polynomial time algorithm exists for that particular problem. And we did a couple of problems like set cover, vertex cover. There is no time efficient algorithm exists for those problems, right? And what was the solution? There is no solution, but we can apply some approximation algorithm by compromising the quality of the solution, right? So approximation algorithm can be used, and we can use greedy heuristic. You may term, please note this term, heuristic. So in real life application, you will see many problems where there is no algorithm or no time efficient algorithm or solution exists. Then we apply some kind of heuristic. And heuristic means it is not guaranteed that you will get the exact solution, but near optimal solution. So we are trying to compromising the quality of the solution. That was, we already talked about that. So today we'll further talk about NP complete and all these details. Okay. So last day at the end, we talked about decision problem and optimization problem. So whatever the problem we are dealing with, we can divide them mostly in two parts. One is optimization problem, like you need to find the minimum of something, maximum of something, that's optimization. We are optimizing the solution. Another one is decision problem. Means we need to make a decision, yes or no, yes or no. Okay, so we'll talk about these two, decision problem and optimization problem. So let's take two examples. So this is one example, subset sum. Another example is popular example, traveling salesman. So what is subset sum? Let's define the problem. Given a set S and a target number T, determine if there is a so let's take one example. Let's S equals to 1, 2, 3, 4. And let's assume T equals to 5, then the and please don't forget to take notes. I'll release another scribe note assignment for this week. So the whole week notes will be submitted by Thursday night. So this is all about subset sum. What is subset sum? There is a set, and so two things are given. Set is given and some value, T, some value of T. Now you need to find out whether there is any subset of that set which that sums to T. So suppose this is your input S equals to 1, 2, 3, 4. This is your whole set, and I gave you T equals to 5. So is there any subset exist that sums to 5, 2, 3, or 1, 4, right? So the answer would be yes. So we are making a decision here, yes or no. And if I say T equals to 8, so is there any subset exist that sums to 8?
Yes.
Yes.
4 plus 3 equals 1.
4, 3, 1.
1, 3, 4. Yeah. Now, if I say T equals to
Yeah.
something like 11,
No.
the answer would be no, right? So it would be a decision problem. You need to say either yes or no. Clear so far? So two things are given for this problem, your set and some value of T. And you need to find out, is there any subset exist which that sums to T or not? Clear so far? That is the problem. Very easy problem. What would be the time complexity for brute force? How many subsets can be there? First of all, how many total number of subsets for this set?
3 to the power 4.
Why 3?
No, 4.
4? How?
2 to the
2
power
to the
4.
power 4, right? 2 to the power 4 number of subsets for this example. So suppose a set with n elements. So what will be the number of subset?
2 to the power of n.
2 to the power n. This is exponential. So brute force will give you exponential time complexity. Although it looks like an easy problem, but it is NP complete, means there is no polynomial time algorithm exists till today which can solve this problem in polynomial time or efficiently. Clear? What is decision? What is subset sum problem? This is subset sum problem. Okay. Now let's move on to traveling salesman problem. First, I'll define the problem. So given a connected, complete complete, undirected, weighted graph. Find a simple cycle that goes to all vertices and has the lowest possible cost. So what is given here? Here a complete undirected graph is given. Okay, so it's a complete graph. One thing, complete undirected graph. So complete undirected graph is given. Your job is to find a cycle, simple cycle. Simple cycle means you will not visit one node more than once, except your starting point. So you need to find a simple cycle. So first job is to find a simple cycle. That means that you will go through all vertices and has the lowest possible cost. Cost means summation of edge weights. So that is your job. Okay. This is traveling salesman problem. Let's take one example. So this is one example. This graph is given. Again, this is traveling salesman problem. A graph is given. What kind of graph? It is a connected complete graph. Complete means every vertex, there will be an edge between every pair of vertices. There should be an edge between every pair of vertices. So it should be complete. It should be complete. Then your goal is to find a simple cycle. Simple cycle. What is cycle? Simple cycle that goes through all vertices. So you need to find a simple cycle that goes through all vertices exactly once, except your starting vertex, and has the lowest possible cost. What is cost here? Cost is edge weight. Cost is edge weights. So you need to find a simple cycle that will go through all vertices and come back to your source vertex and has the lowest possible cost. That is the traveling salesman problem. Clear so far? So for this graph is given. What would be that simple cycle that will give you the lowest possible cost? Do it manually. Find a simple cycle in this graph starting from A. Let's assume you are starting from A. You want to find a simple cycle that goes through all vertices and has the lowest possible cost. A, B, C, D, A. So A, then you go to B, B to C, C to D, D to A. It's a simple cycle and it will give you A to B is 1, B to C is 3, C to D is 2, D to A is 2. So total cost is 2 plus 2, 4, 3, 7, 8. This is the total cost. And this is also simple cycle. Simple cycle means there is a distinct difference between cycle and simple cycle. Simple cycle, no vertex should be visited more than once. See, all vertex, intermediate vertex, visited only once, except the starting vertex, because it's a cycle. That means you have to return to your starting point. Then it would be a cycle. So that's why it is a simple cycle. Clear so far? So this is traveling salesman problem. And here you can think A, B, C, D are some grocery stores. And you need to visit all grocery stores and come back to your home. So A is your home, B is Walmart, C is Kroger, D is Publix. So you need to visit all grocery store in such a way that will give you least possible, lowest possible cost. And you have to come back to your home. Very easy problem. Traveling salesman problem. But still, there is no efficient algorithm exist so far. Why? Just think for this small example, how many ways you can visit all places and come back to your home? You can go A, B, C, D, A. You can go A, B, D, C, A, right? You can go A, D, C, B, A. So how many total possibilities will be there? It would be 4 factorial. Now think, if it is, there is a number. I forgot the number, maybe 20 factorial or something. Only 20 cities you need to visit. It should be a huge number that no modern high-performance computing can solve this. It's so huge. If you follow brute force means you have to explore all possibilities. So 4 factorial means you will explore all possibilities and calculate the total cost and find the minimum one at the end. So if it is n equals to 100, that is 100 factorial or 200 factorial, which is infeasible for any computer in this world, any high-performance computer. So it's also exponential, n factorial. The time complexity for brute force would be n factorial. Okay. So we have discussed 2 problems: subset sum, which gives you exponential time complexity, and it is n factorial, it is also exponential. N factorial, you may consider it as n power n, something like that. Huge number, n factorial. So both are hard problem, you may think. Now see the difference between these 2 problems. This problem is saying has the lowest possible cost. Means you need to find simple cycle that will give you the lowest possible cost. That means what kind of problem it is? Decision or optimization? What kind of problem it is? Decision or optimization? Optimization, because of lowest. You need to optimize that cost. So it's an example of optimization problem. So this is TSP optimization. It is known as TSP optimization problem. Just one thing you need to clear. Optimization means you need to find either lowest, highest, maximum, minimum. So you are optimizing something. That is your optimization problem, like 0-1 knapsack problem, fractional knapsack problem. All those are optimization problems. Now, what kind of problem is this one? Subset sum. Is it optimization problem? Are you optimizing any value? No. It's a decision problem. You are making a decision whether there exists any subset that sums to T or not. Yes or no. So this is decision problem. So is it clear to you what is the difference between decision problem and optimization problem? Clear, right? Okay. Now that is your TSP optimization problem. Can we convert TSP optimization to a decision problem? Can we convert TSP optimization as a TSP decision problem? We'll modify the problem definition slightly, like this way. Means there should be a T where the cost would be less than equals to T. T is a simple, we already find a simple cycle with cost T. So you need to find whether there is such a valid simple cycle or TSP tour. It is called TSP tour. Simple cycle for this problem is called TSP tour. TSP tour. So you need to find whether there exists a TSP tour of cost less than equals to T. Then it will we can make it as TSP decision problem. So let's define it properly. So this one was TSP optimization. Here I am defining TSP decision problem. Okay, before going into that, let me briefly talk about this one. I missed that. It would be better to talk about that one. So this is your graph, and you have seen the brute force will give you order of n factorial. Now think of very intuitive solution of this one. Just think of greedy approach. Can you apply greedy approach here? If you apply greedy approach, what would be the solution? Greedy means the best at this moment. Don't think about the future, right? You will start from A. What is the best one? B, right? So A, then B, cost 1. Then what is best at this moment at B? D, with cost 2. At this moment, what is the best? C, with cost 2. At this moment, you have to return to your home, right? So A. And what is the cost of A? 1,000. That's the problem with greedy. Greedy don't think about the future. And for this particular, although it's an extreme example, boundary case, you may think, but greedy will fail severely, right? Total cost is 100,005, much more than 8. 8 is the optimum one. So greedy always give you some solution, but for this kind of cases, it fails severely. Okay. So we'll talk about TSP decision problem. So we will convert TSP optimization problem into a decision problem. So far, is there any question? So we have talked about what is decision problem with an example, what is optimization problem with an example. Now we'll talk about how we can convert optimization problem into a decision problem. So define the problem given a same complete graph weighted undirected graph. So graph would be there, as well as we'll have some target value and a target T, target cost T, determine if the graph has a simple cycle that goes through all 36 and has a cost less than equals to T. So see how we change the traveling salesman TSP optimization problem into TSP decision problem. So here we have the same complete undirected weighted graph along with a target cost T. Now you need to determine if the graph has a simple cycle that goes through all vertices and has a cost less than equals to T. Clear? So now it is a TSP decision problem, not an optimization problem. We are not optimizing anything. We are making decision whether such path exists, such cycle exists or not. We are making a decision, yes or no. Clear? Now, let's briefly talk about the relation between decision problem and optimization problem. Let's assume you have some solution for this one, efficient solution for this one. Let's assume. So let's assume some solution. This is your black box. You don't know how to do that, but let's assume you have a solution for TSP decision. So some solutions are there. So what are the inputs of this solution? Two things, graph and a target cost value, right? So this is your graph and this is your target cost value. And what is the output? What is an output for decision problem? Yes or no, right? Yes or no, right? Now the question is, can you use this solution to solve optimization problem? Can you do that? Use this solution to solve optimization problem.
Yeah.
Yes, Neil, how?
Like, let me just take the, yes, or like, let's say the target cost is 8, right? And then you can just look at the graph. You
Great.
just give them and come up with,
Great. But how do you come up with 8?
by following the graph. Like,
But how do you come up with that value 8?
you're given it. Like you said, the target cost is 8.
Yeah, but for you don't. Why 8? What can you don't know 8, right?
Right.
Beforehand, you don't know 8, but you know it should be at least 0 because it's an age weight positive edge weight. So we can start from 0. So if t equals to 0, what would be the output? No. If t equals to 0, the output would be no, because no such cycle exists. If t equals to 1, what would be the output? Is there any cycle exist?
No.
Is there any cycle exist? No. If it is 2, what would be the answer? No. If it is 3, no cycle exists, that was 3. If it is 4, no exist. 5, no. 6, no. 7, no. 8, yes. When you reach 8, it will say yes, right? That means you can run this solution multiple times, then you will come up with that optimum value. In this case, it is 8. In other case, it may be 800. But you will reach to that solution, right? If you run this solution multiple times. Is it clear to you? That means you can use this solution of a decision problem to solve the optimization problem. I'm not talking about efficient. I'm talking about the relation between decision problem and optimization problem. So you can use the solution of a decision problem to solve the optimization problem. So it is clear to you. Okay. So far we have talked about decision problem, optimization problem, and using one example, how we can use solution of a decision problem to solve optimization problem. That needs to be clear to you. So clear so far, right?
Yeah.
Okay. So let's move on. Now we'll talk about verification. First, this is the base. I'm trying to create the base. So first you need to understand what is optimization problem, what is decision problem. That needs to be clear. These are our problems. Now I'll talk about verification. It is confusing, that's why I've listed out all topics here. So there is some relation. We will understand it carefully. So first we have understood what kind of problems we are dealing with. One decision problem, another is optimization problem. Now, what is verification? Verification means there is a problem. Just assume there is a problem and I give you some solution. Your job is to verify whether the solution is correct or not. Very easy. Means the problem is you need to sort an array and I give you some sorted array. Some array. You need to find out, verify whether that array is sorted or not. Whether the solution is correct or not. So that is verification. Now the question is, can you verify that solution in polynomial time? Means efficiently. So let's write. So now we'll talk about verification. Given a problem, if someone gives you a solution, can you verify the correctness of the solution in polynomial time? So let's assume your problem is sort and array. This is your problem. And suppose Neil comes up with a solution that, hey, this is my solution. So Neil gives us solution A. Now, James' job is to verify whether solution A is correct or not. But in polynomial time. In polynomial time means efficiently. Not by using brute force or naive approach. Clear? What is verification? Do I proceed? So first we have learned decision problem, then we have learned optimization problem, then we have learned there is some optimization problem where we can find decision problem, and we can use solution of that decision problem to solve the optimization problem of the same kind. Now our next topic is verification. Verification means to verify whether an answer given by someone is correct or not. You need to verify that in polynomial time. So we'll again go back to those two solutions, those two problems, subset sum as well as TSP optimization and TSP decision problem, to check whether we can verify their answer in polynomial time or not. So we'll revisit all those three examples again. So let's talk about first TSP decision, subset sum. So given a set S and a target T, someone gives you a proposed solution S dash. So for subset sum, what are the things which are given? A set and a target value T. Now someone, maybe Neil, gives you a proposed solution S dash. So for example, S equals to 2, 3, 4 and T equals to 7, and Neil gives you S dash equals to 3, 4. So Neil gives this solution, propose this solution. Now our job is to verify whether the proposed solution is correct or not. Clear? How you can verify that? So this is the proposed solution. Proposed solution. Now how can you verify the proposed solution? How can you verify this proposed solution? For this example, just think. Is it correct solution? The set is 2, 3, 4 and T is 7. Now Neil gives you this proposed solution is 3, 4, the subset. Is it a correct solution?
Yes.
If so, how do you know it's a correct solution?
Use my eyes.
Yeah, means which logic you have applied.
This is
Yeah, means for this particular example, how do you know it's a correct solution?
this line.
Don't think about fair. So first 3 plus 4 is 7. So it equals to your target value. One thing, you check that. internally. Also, you have also checked 3, 4 both present in your set. Means it's a valid subset, right? So 2 things you check. Whether it's a valid subset, that is 3, 4 present in your set. At the same time, whether 3 plus 4 equals to 7 or not. For example, S dash, James using his faith comes up with 1, 8. So is it a correct solution?
No, that's not.
No, why?
Because it doesn't equal 7 and it's not even.
Or okay, 1 plus 8 is 9. So it is not equal to t. Or let's make it 1, 3. Is it a correct solution?
No,
Why not?
doesn't
It's
have
not in
seven.
the set.
It,
Also, one's not in this set, so
okay, let's make it 2, 3.
it still doesn't add up to 7.
1 is satisfied. 2, 3 both are present here. 1 is satisfied, but 2 plus 3 is not equals to 7. So you need to check 2 things for verification. And how can you do it programmatically?
No, we already determined the solution.
Very easy. Believe me, the solution is very easy. How do you verify it programmatically?
Check if they're in this set, and then
Great.
check if they add 7.
So how do you check whether it is equals to, it sums to 7?
Add them.
Just add them. How much time you need to spend for that? Just add all elements of that subset
Yeah. So,
in. And how do you verify whether they present in your set or not?
search.
Search means you will use 2 loops. So for one for S dash, another for S, and check whether that element present in both sets or not. So you can use 2 loops, right? Is it clear? These 2 loops. So you need to traverse S dash, at the same time you need to traverse S and check whether all elements of S dash present in set S or not. So you need 2 loops. It's not difficult. So how much time it will take? Two loops means n squared. One loop means normally n. 2 loops means n squared. 3 loops means n cube. 4 loops means n to the power 4. Normally, 1 loop means n. Means you are traversing all elements. If number of elements is n, you need to traverse all n elements. So there are 2 loops. So time complexity would be n squared. So how much time you need to spend to verify the solution, this proposed solution is correct or not? N squared. Let me say again. How do you know the proposed solution is correct or not? You need to check 2 things. First, sums up equals to, if you sums all elements, it should equals to t, which is order of n. Next, you need to check whether it's a valid subset. Means all elements of this proposed solution should be present in your set, actual set, right? You need to check both. And to verify that, it is only n squared. You need to just use 2 loops. Using 2 loops, you will get the solution.
So if, let's say that the solution 1, like t doesn't equal whatever, right? Do you just kill it then?
Say again.
All right, so let's say that you're given t equals 7, right? And then you're given 1 and 3, it doesn't equal 7. Do you still need to go to step 2? Because you just disproved it using the first step.
Okay, 1, 3. Yeah, you don't need to check this one.
So that would just be n at that point, correct?
Yeah, but we will think about general cases, not a particular case. We should think about the worst case.
Okay.
Okay. You are saying best case. That's also good thinking that I'm impressed that your thinking is on the right way, right direction. So the time complexity to verify whether the proposed solution is correct or not is n squared, which is polynomial, right? So for this decision, subset sum is a decision problem. And to verify the solution, proposed solution for this decision problem is polynomial. So we can verify the solution of this decision problem in polynomial time. Right? Yeah. This is one important conclusion. So we can verify. So subset sum is verifiable in polynomial time. This is important. It is verifiable in polynomial time. Clear so far? Now let's talk about TSP optimization problem. This one. Can we verify in polynomial time? Let's assume I have given you some solution S dash. S dash. Can you verify that's the optimal path or optimal cycle? Can you verify that? Yes. Can you verify that in polynomial time? Just assume, let's take another example. There is an array. If our goal is to find out minimum from that array. Okay. That's the problem. Finding minimum in an array. Now there is a large array. I said that minimum is 15. How do you verify whether 15 is the minimum or not?
You have to go through all the other solutions.
And there is no efficient solution exist.
No.
Then can you verify inefficiently?
No.
No. Because just think, you don't know what is optimum. There is no efficient solution to know the optimum solution. So how do you know if my proposed solution will give you optimum value or not? How do you know efficiently? Because if you know the answer, that means you have some algorithm which will calculate that optimum value efficiently.
Yeah.
And in reality, there is no such algorithm exist. So for this optimization problem, it is not possible to verify this solution, a proposed solution in polynomial time. Clear the concept? So for optimization, this TSP optimization, you cannot verify the proposed solution in polynomial time. So let me write, cannot be verifiable in polynomial time. This is for TSP optimization. We cannot verify the proposed solution is correct or not in polynomial time. It's not possible. Clear? Now let's talk about TSP decision problem. If I give you some solution, can you verify? Suppose I give you some value, some simple cycle. Now what you need to check whether the cost of that cycle is less than equals to t or not. So is it possible?
Yes.
Very easy. In polynomial, just sum up all edge cost. That should be less than equals to t. So TSP decision problem is verifiable in polynomial time. So what we have observed, this is a decision problem which can be verifiable in polynomial time. This is another decision problem which can be verifiable in polynomial time. But it is an optimization problem which cannot be verifiable in polynomial time. So in general, we can make a comment. Normally, all decision problem can be verifiable in polynomial time, unlike optimization problem. The problem with optimization problem is to know the optimum value. If you don't know the optimum value, how can you verify that solution? That's why optimization problem are not generally verifiable in polynomial time. Clear so far? So far we have studied what is decision problem, what is optimization problem. Then we studied how we can verify proposed solution for decision problem in polynomial time. At the same time, is it at all possible to verify proposed solution of an optimization problem in polynomial time, which is not possible. Clear? This needs to be clear. Are you with me?
Yeah.
Great. Now we'll define what is P, what is NP. Now you'll understand what is NP. NP is those problems which can be verifiable in polynomial time. So it leads to complexity classes. So all P, NP, those comes under complexity classes. NP here, NP stands for problem which are verifiable in polynomial time. That belongs to class NP. And what is P? All the problems we studied before midterm comes under P, means where exact solution is available which are efficient, means which gives you solution in polynomial time. Means it's an easy problem normally. So let's define that. So before that, make sure that your concept of decision problem, optimization problem, and verifiability in polynomial time should be clear. Any question till now? It is clear to all of you? Okay. Let's define complexity classes. First class is class P. So whatever solution we have studied before midterm, all comes under P. Means efficient solution exist. Means polynomial time solution. Like DFS, Dijkstra, Prims, Kruskal's, then all sorting algorithm, smart sort, quick sort, etc. All comes under this class P. Means we already have good solution, efficient solution for those problems. Efficient means polynomial time. Again, polynomial means the form should be n to the power k. K should be some value. K equals to 0 to any value. N, n square, n cube, n4, n5, anything. That is polynomial. So this is class P. It's very easy. You all know what comes under class P. Then let me introduce NP. actual NP is problems which can be verifiable in polynomial time. Then we'll call it NP class, class NP. NP class is clear to you, like previous example, subset sum decision problem. That can be, the solution can be verifiable in polynomial time. That means it comes under NP class. At the same time, TSP decision problem can be verifiable in polynomial time. So it comes under NP class. Clear so far? Now tell me whether a problem comes under P. What is the relation between P and NP?
We don't have a solution that exists for NP, an efficient solution that exists for NP, but you can verify it.
Yeah, that is NP. And for P, just think of BFS.
We use P to verify NP.
Okay, let me take one example. There is a graph. You need to traverse the graph. And I gave you some solution. Can you verify whether that's a correct solution or not? How? BFS or DFS? Because already known solutions are there. So you can just apply BFS or DFS to verify my answer. Or I gave you some sorted sequence. You need to verify whether it's a correct sorted sequence or not. How can you verify that? By using any sorting algorithm, merge sort, quick sort, anything. Or I give you some single source shortest path solution. You can apply Dijkstra just to verify whether that's a correct solution or not. That means, can I say all problems comes under P can be verifiable in polynomial time? Right? All problem comes under P can obviously verifiable in polynomial time. Because which is harder, getting the solution or verification? Which is harder?
Getting the solution.
Getting the solution is much harder. Verification is much easier. But getting the solution is harder. So for this class, all solution, all problem has efficient solution. So obviously they can be verifiable in polynomial time. So P is a subset of NP. Right? P is a subset of NP. Because all problems which comes under P can be verifiable in polynomial time. That means it also belongs to NP. So if we draw like this Venn diagram, this is NP, then P is this part. So subset sum comes under here, subset sum or TSP decision problem, which is not P, which doesn't comes under P, but it is under NP class. And under P, you have sorting, you have searching, BFS, those things. Is it clear so far? Clear so far? Again, I am asking.
Yeah.
Okay. So P is a subset of NP. Can we say P equals to NP?
No.
No, because so far, no, with some conditions. Is it clear what is P equals to NP? So far, we have some problems which doesn't have any efficient solution, but we can verify them in polynomial time. So far. But in future, there might be some solution, efficient solution comes, right? So this is an open problem. Till today, no one knows the answer. It's an open problem.
Oh, yeah.
We don't know whether P equals to NP. It's an open problem. No one knows the answer.
Get $1 million and you can prove it.
Right. True. It's a, if you prove it, whether P equals to NP or P not equals to NP, you will get almost similar kind of Nobel Prize. No one knows the answer. But the question, the concept is clear to you, right? What is P, what is the NP, and what is the relation? So far, whatever we know so far. So it's an open problem. So this two part is clear to you. What is P, what is NP? And why I need to go through all those details? Because I first need to introduce you what is decision problem, what is optimization problem, and what is verification and verifiability in polynomial time. Then only I can introduce you with NP. Otherwise, I can't introduce you what is NP. If I directly tell you NP is this, you can't understand, right? That's why I have to create this base. So you have understood P, what is NP right now, right? Okay. Any questions so far? Is it too difficult? Conceptual, but not too difficult at all. But you need to revise. And take this note, flow. Flow is always, when we need to memorize something, we need to make a story, connection. If you lose that connection, you can't memorize anything. There should be some connection. Okay, this is NP complete. I have understood. Then there is two problems. One is decision problem, another is optimization problem. And we can convert an optimization problem into a decision problem. Then verifiability. Can we verify the solution in polynomial time? Then comes NP. There should be some flow. If you understand that flow properly, your memory will help you to memorize the whole things. You don't need to provide lot of efforts to memorize. So it is clear. What is P, what is NP? Great. Now we'll talk about NP complete, NPC, NP complete. I'll not give you any attendance. No.
Okay.
So NP complete. So we have understood P, NP, and NP complete. Previously, I gave you informal definition. Again, I'll give you informal definition because I need to create base. Then I can give you formal definition of NP complete. So NP complete, let's give another informal definition. So NP complete, those problems which comes under NP, which comes under NP class, and it is the hardest problem. So if we draw a graph like this, and this is your hardness, then P comes in the bottom part. This is your class P. Then this is your NP. The whole thing is NP. And the top part is the top part of this is NPC. This is the hardest part of class NP. Okay.
You call it the hardest part when there's one literally called NP hard.
No, NP hard is different. I'll come to that point. we have not discussed about NP hard. So this is NP, and inside NP, you have NP complete, which is the hardest part of NP. Okay. Now let's informally define NP complete. So the hardest problems in NP, and another thing is X is NP complete if all problems in NP is reducible to X. Here comes another topic, reducibility. So it is saying X is an unknown problem. Just think X is an unknown problem. Then we'll say X is NP complete if all problems in NP can be reducible to the problem X, to this new problem X. What is that meaning? What is the meaning of this? Let's discuss. Reducibility, reduction. Let's assume in this classroom, just think. We will divide this set of people into two sections. One is people with 6 feet height and people with below 6 feet height. Two sections. So let's assume this is the people with maybe 5 feet. It is more meaningful here. People with 5 feet, more than 5 feet. So everyone will comes under this set. So there are many people are here. Okay, who is the tallest? What? Maybe you. What is your name?
Jared.
Sorry.
My name is Jared.
J. Yeah, Mr. J.
So
Let's assume all have same height. Okay, all have same height, maybe 5 feet. Now some new guy comes up here. X. X is a new guy, comes here. Now I need to check whether he or she belongs to this set or not. How can we check that? I can compare X with J. If X is at least J, then I will put X in this set, right? Otherwise, I'll not put him or her in this set. This set is, just think, I have used one analogy. This set is nothing but NP. This set is nothing but NP. I have some new problem X. I will compare X with some known J, Mr. J, who is already known to be of height at least 5 feet. So suppose the problem is subset sum. If I know X is at least as hard as subset sum, then obviously X should belong to this part, right? So that is reduction. That means this is known problem. We will reduce this problem to X. That means we'll prove that X is harder than this problem. We will prove X is harder than this problem. Then obviously X should be there, right? If we prove X is harder than this problem. That is reduction. Is the concept clear? What is reduction? Just take note of this example which I took, height example. Otherwise, you will be confused again. That height example is important. Then it will be clear. Otherwise, you will forget again the logic, where the logic comes from. So we have introduced reduction or reducibility. What is reducibility? X is an unknown problem. We don't know what is X. where X will belong to. I will compare X with some known problem which is already in NP class. And we'll prove that X is harder than that known problem. Then we can say X is NP complete. Clear, right? Okay, we can take another example. This is linear equation, quadratic equation. Okay, let's assume this is the solution for cx square plus bx plus e equals to 0. This is some solution you have. So it takes 3 input C, D, and E, and it calculates what is X. Right? The solution will calculate what is X. Now, just think, can you use this solution to solve this problem? Can you use this solution to solve this linear equation? Can you do that?
No.
No? If I say C equals to 0, D equals to A, E equals to B, can we do that? Yes. It's the general case of that equation. It is a general case, one case of that equation. So we can use the solution of this equation to solve this problem. How? C equals to 0, D equals to A, E equals to B, we will get the solution. That means we are reducing this problem to solve this problem. We are reducing this problem to solve this problem. Clear so far? Which one is harder? That one, right? This one is harder. So just assume this is known to be an NP complete. So where it will belong? If it is NP complete, just assume there is no efficient solution exists for this one. Then can you get an efficient solution for this one? No. That's why reduction concept is important. So we can say A is less than equals to B. That means A is reducible to B. So we'll continue this discussion next day. So less than equals to, I should not say like this way. Less than equals to doesn't mean that A is smaller or something. You may think A is less harder compared to B. Means B is harder than A. We'll continue next discussion from here, reduction, and then we'll talk about NP complete as well as NP hard.